Okay, now that we're done with building a kaleidoscope, let us move on to refraction. So in reflection, we thought about what will happen when a light ray reflects across a boundary. But now in refraction, what happens is that the light ray will pass through the boundary into the next medium. So for example, a light ray can pass from air and move into water. Now what will happen is the light ray will actually change direction. So have you ever put a straw into a bottle of water and seen the straw bend in its shape? Or have you ever seen patterns of light in the swimming pool? This is all because light is changing direction when it passes from one medium to a next medium. But why does this principle of refraction occur? This is because the light rays travel at different speeds when it moves in the different mediums. So we can call refraction the bending of light when a light wave enters a medium where its speed is different. Now let me give you an example. Light moves much faster in air than water, and it moves even slower in glass. So we can demonstrate this using a prism. So you all should know that when we pass a beam of white light into a prism, it will split into its many different colors. Now this actually happens because of refraction. So light rays move much slower in glass than in air. So when we pass the white light into the glass, the light rays start moving slower. What's special here is that some colors, like blue, move a lot slower in the glass than other colors like red. So what will happen is the blue colors will move slower than red and will lag behind the red colors. This creates a divergence in the light rays. And what will happen when the light rays come out of the prism is that they will actually split colors and we can see a spectrum of light rays. So this acts, so you can see a mini rainbow. Let's demonstrate this principle using an activity. So I need all 4 of you from the back tables to line up in threes in the center of the lab. We have a sticky zone behind this line of masking tape, where all of you should move slower. Now all of you represent the light ray as you're moving through the lab into the sticky zone. Now the masking tape represents the boundary between the medium that you're moving faster in and the medium that you're moving slower in. And the sticky zone represents the medium that you, the light rays, are moving a lot slower in. So as you move down the lab, you will see what happens when you pass through the boundary into the sticky zone. Okay, after the activity, you can see this happening right here in this diagram, where the left side of the light ray will reach the interface first and slow down. The right side hits the interface at a different time, so it changes direction, as you can see. So when the left side hits the medium first, it starts moving slower before the right side. So the left side of the beam will actually slow down first. This causes the light ray to bend and move unevenly across the interface. This causes the entire light ray to change direction and bend when it enters into the next medium. So we can see here in the diagram that as the light ray moves from air into glass, it actually changes direction and doesn't move exactly in a straight line across the interface. Now, do you remember the normal from reflection? This actually applied to refraction as well. The normal is an imaginary line which is perpendicular to the interface at 90 degrees. So when the incident ray passes through the interface or the boundary into the next medium, refraction occurs. And this forms the refracted ray, which travels in the second medium. The angle of incidence is the angle between the incident ray and the normal, and the angle of refraction is the angle between the refracted ray and the normal. Over here, you can see that the angle of incidence is a lot bigger than the angle of refraction. And this is because refraction has occurred, and the light ray has bent, changing direction, and the light ray has moved closer to the normal in this case. Note, however, that the light ray can actually move away from the normal, as we will see in other cases. So in this case, the angle of incidence is bigger than the angle of refraction. Now we need a way to represent how fast light will move in a certain medium. Now the way that we represent this is by the refractive index. Now in some mediums, light moves a lot faster than in other mediums. For example, light moves faster in air than in water or glass. So we can see in the table on the left here that air has a refractive index of 1 and water has a refractive index of 1.3 and that glass has a refractive index of 1.5. So what we can see here is that as the refractive index is increasing, light moves slower in that material. So for example, in diamond the refractive index is 2.417. This means that light moves 2.417 times slower in diamond than in air. Wow, that's a lot slower. So remember that, so similarly, if the refractive index is lower, light travels a lot faster in that material. Using the table of values over here, we can find that light travels 1.6 times slower in glass than in air. Now for those interested, we can calculate the refractive index by dividing the speed of light in a vacuum by the speed of light in the medium itself. So for example, since light travels 1.5 times slower in glass than in air, the index of refraction in glass will be 1.5 as well, by this ratio. Now let us look at this simulation. From the simulation just now, we can see that as light moves from a material where it moves from a higher speed to a lower speed, the angle of incidence is a lot bigger than the angle of refraction. But the other way around can also happen, where if it's moving from a place where it's moving slower to a medium where it's moving faster, the angle of incidence will be smaller than the angle of refraction. So what is happening here is that if the angle of refraction is smaller than the angle of incidence, the light ray is moving closer to the normal. But if the angle of incidence is smaller than the angle of refraction, then the light ray is moving away from the normal. So in summary, for a light ray moving in materials from a lower to higher refractive index, this means that the light ray is traveling faster and then is moving slower. Therefore, the angle of incidence is greater than the angle of refraction, and the light ray is moving closer to the normal. Whereas, for a light ray moving from a higher to lower refractive index, the light ray is moving slower, then is moving faster. Therefore, the angle of incidence is smaller than the angle of refraction, and the light ray is moving away from the normal. Now, remember that as light moves to a medium where it travels faster, it refracts and bends away from the normal. Correct? So for example, in this diagram on the left, the light ray is moving from water to air. So it bends away from the normal, and the angle of refraction is a lot bigger than the angle of incidence. So when I try increasing the angle of incidence little by little, the angle of refraction will also increase. So if I keep doing this, the angle of refraction will eventually increase to 90 degrees at a certain angle of incidence. This angle of incidence is a special angle and we call it the critical angle. Now what will happen if I keep increasing the angle of incidence? Can it go beyond 90 degrees in the second medium? Actually it cannot, and what will happen here is that the light ray will not travel into the next medium and will remain internally into the first medium. So what will happen instead is reflection. So since it happens total, and since there is no light rays going through the next medium, we call it total reflection, as there is no escaping of light rays occurring. Therefore, this phenomenon is known as total internal reflection. This is basically just reflection, which happens when the angle of incidence is much bigger, when the angle of refraction is bigger than 90 degrees, and therefore refraction cannot occur. So reflection happens instead. Now let us look at some demos.